Lesson 1.7, Modeling with Functions. In this lesson, we're going to take many different real-life situations, create equations to model that situation, and then solve. In the first example, we're going to write the area of a circle as a function of many different items. Okay, first we're going to write it as a function of its radius, then its diameter, and then the circumference. So first, area of a circle. Our most basic equation that we all remember is area is equal to pi r squared. Okay, this is an area of a circle as a function of its radius. So as the radius changes, the area is going to change. In part B, we want to write it as a function of its diameter. Well, we know the diameter is equal to 2 times the radius. If we would solve and get the radius by itself, this is the same as saying the diameter divided by 2 is equal to the radius. So in our first equation where we have the radius, we can divide or substitute in this equal value. So we have the area is equal to pi times d over 2 quantity squared. And if we simplify that out, this exponent gets distributed to the numerator and denominator. So this becomes pi over 4 times the diameter squared. Now we have an area of the circle as a function of its diameter. In part C, we want to write the area as a function of its circumference. We know the circumference is equal to 2 pi r. If we would isolate r by itself, we would get the circumference divided by 2 pi is equal to the radius. Now, same thing we did before, substitute that expression in for the radius. So we have area is equal to pi times c over 2 pi quantity squared, which is equal to, we have pi over 4 pi squared times c squared. The only thing we could do with this expression is simplify out some of those pi's. Okay, we have a pi in the numerator and we have a pi squared in the denominator. So we could cancel those out and we'd be left with c squared divided by 4 pi. So now we have 3 different equations for the area of a circle written as a function of its radius, diameter, and circumference. In this next example, we have a square of side x inches being cut out of each corner of an 8-inch by 15-inch piece of cardboard, and the sides are folded up to form an open-topped box. Okay, so we have our piece of cardboard, 8 inches by 15 inches. In each corner, we're cutting out a square x inches wide, and then we would fold this box after we cut out each corner along the dotted line. Okay, those are going to be their folds, fold them up, and we create a box. For part A, we want to write the formula V of the box as a function of x. So we have the volume is equal to, remember if we're talking about volume of a box, we have our length times our width times our height. After we make these cuts and folds, the width of our box is going to be 8 inches minus x, or we could simply just write 8 minus 2x. Similar for our length, we started with 15 inches minus x, or we have 15 minus 2x. And then the height of our box after we make these folds is going to be a height of x inches. So we have 8 minus 2x times 15 minus 2x times x. For part B, we want to find the domain of V as a function of x. If we look at the equation we have, if we would multiply this out, we would have a polynomial of degree 3. And we know the domain of polynomials are negative infinity to infinity. But because we have a story problem, we have restrictions on what our domain can be. For instance, if we look at x representing the height, we know because we're talking about lengths and distances that this value cannot be negative. So for our domain, the smallest value we can have is 0. Okay, technically, yes, we can have a box with a height of 0, It technically wouldn't be a box, it wouldn't have any volume at all, but it can be equal to 0. It just can't be any negative value. Also, if we look at our first expression, which represents the width of the box, we know that value cannot be negative as well. So we said 8 minus 2x must be greater than or equal to 0. If we would solve this over, we'd have negative 2x must be greater than or equal to negative 8. And then if we would divide, we would have x is less than or equal to a positive 4. Okay, so first I would subtract this 8 to the other side, then divide by a negative 2. If we're dividing by a negative, remember the sign on our inequality has to flip. So because of this restriction, we can't have any values for x that are greater than 4. So the domain for this polynomial ends up being 0 to 4 with those endpoints included. Part C, use a graphing calculator to find the maximum volume the box could hold. So I graphed this function going from 0 to 4 and 0 to 100. If we graph this, go to second, calculate, find the maximum value, we could see that occurs at 90.7 cubic inches. Okay, so that's the maximum volume that this box could hold. And if we look, we could see our x value is 1.67, which is 5/3. So for part D, how big should the cutout squares be in order to produce the box of maximum volume? We can see that the cutouts for each corner, okay, the square that we're cutting out should have dimensions of 1.67, or that is the same as 5/3 inches. Okay, so the maximum volume we can see occurs when x is equal to 5/3. So if we're trying to create the box that has maximum volume, that is the dimensions each square needs to be that we cut out of each corner. Grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? First, since we're dealing with the volume of a cone, we need to recall that formula. We have volume is equal to 1/3 times pi times the radius squared times h. In this problem, we know there's a specific relationship between the radius and the height of the cone. We know the radius and height will always be equal. So we can rewrite this expression as 1/3 times pi times the height cubed. Since the height and radius are equal, we can substitute h in for the radius, so we'd have h squared times h, which is h cubed. Currently, we know the cone is 1 foot tall, which is the same as 12 inches. So to calculate how much volume is currently in the pile, we take v equal to 1/3 times pi times 12 cubed. We know we have to write this in terms of inches rather than feet because in the beginning of the problem, our rate was in inches. So we have to keep the units the same. And if we multiply this out, we get 576 pi inches cubed. We're dealing with volume. We know that's a cubed dimension. So this is how much grain is currently in the pile. We need to determine how much extra grain is going to fall in the next hour. So in 1 hour, that's equal to 60 minutes. And we're told it falls at a rate of 8 cubic inches per minute. So we're going to multiply that by 8 to get 480 inches cubed. So we know how much grain is currently in the pile. We know how much is going to be added in the next hour. So we can set up an equation to solve for the height of the pile. If we take how much there currently is, plus how much is added in the next hour, we can set that equal to our expression and solve for h. So we set our expression for the volume 1/3 pi h cubed equal to the amount we started with in the pile plus the amount we know is going to be added in the next hour. Now all we have to do is use algebra to isolate and solve for h. So first we can get rid of that 1/3 by multiplying by 3 to each side. So we have 3 times 576 pi plus 480. Next, we would divide by pi. So we have 3 times 576 pi plus 480. And then we have all of that divided by pi. And last step would be to take the cube root of each side of this equation. If you do that, we get h is approximately 12.98 inches. Okay, so 1 hour, we started, it was 1 foot tall. In 1 hour, it would be 12.98 inches, which would be 1 foot and 1 inch. To end this lesson, we're going to discuss regression curves, which are simply curves used to represent a data set. In Algebra 1, we worked with these. We found the line of best fit. We just dealt with linear equations when talking about regression curves. There are many different types of regression curves based on the type of data we have. Okay, some of the most common ones are going to be linear, quadratic, cubic, natural logarithm, and exponentials. Okay, if you go on your graphing calculators, go into the statistics part, we can see all of these different types of regression curves that we can use. Okay, this is a little longer of a process and more complicated, so we're going to go through some of these together in class.